Good afternoon. Welcome to the second of the two talks Allison Kaptur is giving this session. Allison works at Dropbox. Please give her a warm round of applause.
Hi, thanks to everyone who came here or stayed here for this talk. Today we're going to talk about exploring is never boring, understanding CPython without reading the code. As Esther mentioned, I'm Allison Kaptur. I'm currently working at Dropbox in San Francisco. I used to work at the Recurse Center in New York City, which you may know by the name Hacker School. It rebranded about 2 weeks ago. And Recurse Center is not a boot camp. The idea is that it's like a writer's retreat for programmers. So if you've been to the PyCon sprints before, it's a little bit like doing 3 months of that. So people who already know at least some programming get together and work on whatever it is that they're excited about. And I say this bit to give you a little bit of context for the problem that we're going to solve today, which I bet you can relate to. So in the course of facilitating at the Recurse Center, I talked to a lot of people who were in the following situation. They'd learned a little bit, or maybe a lot, of Python, and they knew how to make things with it. They'd done a bunch of projects. And then at some point, they started to want to dig deeper. Say, like, well, how does Python work under the hood? The word really appears in a lot of these questions. Like, how do lists really work when you append to them, and so on? And very often, they found it hard to get started. They sort of struggled to get purchase on the giant surface area that Python presents. And so if this sounds familiar, then this talk is for you. And today I'm going to talk about some strategies that you can use to deepen your own understanding of Python, some pitfalls that you can hopefully avoid. The goal is to give you a set of tools that you can use on your own, and we'll look at some examples in CPython, but for the most part, these are strategies that you could use on any code base. So first, a brief word about why you'd want to spend time understanding the internals of Python. And I want to say explicitly that I don't think that you have to do this to be a great programmer, or even to be a great Python programmer specifically. I think the best reason to do this is what's in the title, that it sounds like fun to you. The idea that you have to me, sort of is a turtles all the way down approach. Like if you say, well, you have to understand the internals of Python, well, half of it's implemented in C, so do you have to understand C really well, and then you've got a computer underneath that, so what about hardware and memory? And I basically don't think that that's strictly necessary. So the main reason is that this is fun. I think it's really fun. Hopefully it sounds like fun to you. I've had a great time over the last year or so digging in on bytecode and the bytecode interpreter, which I think about. Can I actually get a quick show of hands for who was in the room half an hour ago? OK, that's like maybe half or more. Great. So I find it very powerful that you can take this really complex project that you've been treating as basically a black box, and you can start to break it down. You can understand the pieces. You can figure out why certain decisions were made the way that they were, and why certain limitations exist the way that they do. I think that's all very powerful and cool. I'm not going to talk at all today about contributing to Python. Contributing is great, and you should totally do it if that sounds like fun to you. I think that contributing presents a different set of challenges than the one that I want to focus on today, which is understanding a code base. Contributing is harder in some ways, particularly tooling and setup. Very often you end up in some sort of bewildering install hell that you have no idea how to extract yourself from. One of my favorite Python mailing lists is Guido complaining about a change made to a recent module that turns out to be a side effect of his upgrading to Mavericks. So, like, this stuff is hard. The other piece that's harder about contributing is that there's all this restrictions around culture and communication and that sort of thing that just don't exist if you're not working with other people. Contributing is easier in some ways than sitting down to understand a code base, too, and particularly in scoping a project. If you're contributing to an existing project, you probably have one thing in particular that you're trying to do. And if you don't have one thing in particular that you're trying to do, the first thing you will do is get one thing that you're trying to do. If you're sitting down to understand a code base, it can be a lot harder to narrow the scope. OK, so I'm not going to talk today about the dev guide, or about the bug tracker, or how to submit a patch, or anything like that. If you want to follow up with that later, here's the link to the official dev guide, and I think there was also a great talk earlier today that you can catch the replay of, and that's all I'll say about contributing. OK, so you're sitting down with a new code base, and you're setting out to understand it. I'm guessing that everyone in the room has heard one particular piece of advice. Read the code. Lots of folks will tell you to read the code. And this isn't necessarily bad advice. I just think it's not always very helpful. And you might have tried this, right? So you go to python.org and you download the source, and you open it up in your text editor of choice, and now what? Now you're staring at like all of these files, and many of them are thousands of lines long, and half of them are in C, and you have no idea where to begin. And it's very easy at this point to get lost. And this is especially true when you have a broad scope. When you say, I want to understand more, dig deeper, but you don't have anything narrow yet that you're focused on. You don't yet have particular sub-goals or areas of interest. And it's also very easy at this point to waste a lot of time. I mean, you're like looking over different files, and you're never really getting a foothold. So both of those are bad outcomes. And this is my objection to the idea of reading the code. I think it's just not a very helpful way to think about interacting with a code base, particularly one that's as large as Python. If you're thinking about reading, it draws analogies in ways that are not constructive for the learner. In the reading that you're used to, if you're reading an article or a novel or your Twitter feed or whatever, there's an order of content, right? You probably have to read the things that happen first to understand the things that happen later. And finally, thinking about this experience as reading, I think undersells it pretty significantly. You should expect that the first time you try to do this, it is going to feel really hard. And if you are thinking of that as reading, it's going to be really discouraging for you. Now, understanding a code base in this way is a specialized skill. And the good news about that is it means that you can get better at it with techniques and particular improvement. But if you're thinking about this as reading, you should expect that it will be very challenging. And calling it reading really undersells that. Just to emphasize this point a bit, there's a great short paper called How to Read a Paper. And spoiler alert, it does not say if the paper's in English, start at the top and go left to right, top to bottom. Right? There's a different set of strategies than that. And reading a paper, even a technical one, is a lot closer to the reading that we're used to, like reading a book or an article, than reading code is. So if you believe that reading a paper is a specialized skill, and you should go read this paper, then you should absolutely agree that reading a code base is a specialized skill, and we should interact with it in a different way. Okay, so consuming information in this way is a skill. You can get better at it with strategies and techniques, and reading is not necessarily a helpful mental model of what we're doing. So today I want to talk about a few mental models that I believe are helpful for digging into the innards of Python that go beyond read the source. These two strategies are sort of guiding metaphors that you can use for interaction with an unfamiliar code base. And for each of these, I'll sort of define the strategy and suggest some tools that you can use that fit into that model. And we'll look at a brief example of putting that strategy to work. So the first way that we can think about interacting with our code base is deliberate observation. And this was really well articulated by Peter Siebel in a blog post, I believe it was last year. And part of it reads, "Code is not literature, and we are not readers. Rather, interesting pieces of code are specimens, and we are naturalists." And he goes on to say, so instead of trying to pick out a piece of code and reading it and then discussing it like a bunch of comp lit grad students, I think a better model is for one of us to play the role of a 19th century naturalist, returning from a trip to some exotic island to present to the local scientific society a discussion of the beetles they found. Look at the antenna on this monster. They look incredibly ungainly, but the male of the species can use them to kill small frogs, in whose carcass the females lay their eggs. So the naturalism model is very different from the reading model. It means that you're considering the environment that the code is inhabiting. You take into account history, some amount of evolution of the code, and you remember that not everything about the code is necessarily deliberate or intentional. So back in college, I studied astrophysics, and my undergrad thesis was some observational astronomy. And astronomy is really interesting to me as a scientific discipline because there's basically no such thing as experimental astronomy. There are three ways of learning about the world, right? The first is theory, sometimes affectionately referred to as the Feynman method, where you write down the problem, and then you think very hard, and then you write down the solution. The second way of learning about the world is through computer models, basically. And then the third is just looking at what's out there in the universe and happens to be sending photons towards Earth and hopefully hitting telescopes. Those are your only options. So if you're doing observational astronomy, the single most important question you can ask yourself is, why are we seeing what we're seeing? So why do we see supermassive black holes near weird-looking galaxies? And in that case, the answer is because weird-looking galaxies are interesting, and we've been pointing telescopes at them for a long time. And if you point the telescope somewhere else, then you see the supermassive black holes there too. I can go on for quite a bit about this. The scientist in question is named Halton Arp, and I'd love to talk more about that. So this way of thinking is almost the opposite of reading, right? So if you're reading a text, usually it is not designed to deceive you. It was probably built for you to read it. The author isn't actively trying to be misleading or confusing or anything else. But code is not built for you to read it. And I realize that this is a somewhat controversial statement. And I currently work with, and have worked with before, a lot of great programmers who set out with great intentions and have good skills. And the code is really readable and clean and awesome. And then reality hits in some manner. You either have optimization problems, you have to get performance up, or you have deadlines, or you have edge cases that you have to handle, and sometimes you have all three of those things at the same time. And so the code ends up not being as clean as you would like for it to be. So what does it look like for you to think of yourself as an expert observer of your code base rather than as a reader? It frees you up to sort of be more targeted, to dip in and out, to look across history, and also to see different levels of structure. So let's look at some specific tools for accomplishing that. One great tool for digging into the Python codebase is the Inspect module. This will take you right to the source code of anything that's implemented in Python without you having to do a ton of searching. So here I'm looking at the source code for random.choice, which turns out to be a one-liner. And so the way that this is implemented is it indexes into a sequence using random.random times the length of a sequence. So there are at least three cool things about doing this. The first one is it's a one-liner that we can understand in less than a minute, which is really satisfying. The second thing is that there's a comment that says, this raises an index error if the sequence is empty. This does not appear in the documentation, although it would be a reasonable expectation given the way that the documentation is phrased. So this is good to know. And the third thing is that choice appears to be a method, so it takes self as a parameter, even though we're calling it like it's a module-level function. So what's up with that exactly? And the answer to that question is really interesting, and maybe we can come back to that in Q&A if people want. But in under a minute, we can understand the implementation, we can learn about an edge case, and we found this thread that we can pull on if we want to pursue this further. So you might have tried to use the Inspect module before and gotten this sort of mystifying output. The one bummer about the Inspect module in the standard library is that it doesn't work for things that are not implemented in Python. So if you accidentally call it on a built-in or something else that implemented in C, it just falls down. And you can't tell if something's implemented in Python or C ahead of time without just knowing. So a friend of mine, Puneet Giganti, has written a tool called CInspect, which is a great hack that makes inspect work for also C-implemented code. And here's a link to that if you want to check it out. I think it's not completely polished at this point, but it's very fun and it works a surprising amount of the time. And I also take a lot of pleasure in my Python REPL suddenly spitting C code at me. If you want to check that out, here's the link. So another way you can be an expert observer is to look at history. You have the full history of the Python codebase available to you, so you can use early code to understand the code that you're looking at today. And this is particularly useful in Python. Python historically has had a reputation for being really clean and readable C code. So you could sit down with, say, the interpreter and follow along without really knowing exactly what's happening ahead of time. And decades later, that is less true than it used to be. And to be clear, that's perfectly reasonable. Most of what's going on is that there's some optimization that's going to speed up the execution of everyone's Python at the cost of making the interpreter more complex. That is almost always the right decision to make. But so today, the result is that the interpreter is much harder to get a foothold on than it was 10 years ago. That's just reality. But you are not limited to the code that's in front of you. You can start your exploration in an earlier version. You can take a field trip to the land where Python was really clean and readable C. Closely related to history is looking at actual changelogs. For Python in particular, which uses Mercurial, you'll want some incantation like this one. And this will give you a patch that introduced a particular line of code, and the author and the commit message and so on. And this is really useful to be understanding the context in which the code was introduced. So was this line of code part of a bug fix? Was it part of adding a new feature? Was it part of refactoring that rearranged things? And looking at the entire patch can often be a really instructive exercise. Another possibility is to look at the internal structure of the code. And for Python, there are lots of different levels at which we can look at the code. There's sort of this source code level, but you could also look at like the AST, for example, or you could look at where the grammar is defined, or you could look at the bytecode interpreter. And sometimes one of these views will be more illuminating than the original source code. Just to take an example of that, this is a great bit of Python trivia, courtesy of my colleague David Uresti at Dropbox. Does anyone want to take a guess for what this evaluates to? If you're in the back, this says false is false is false. I'm hearing a lot of falses. Does anyone want to give an explanation for why false? Right, so false is true. True is false, therefore false. Basically parsing it like this. Totally reasonable guess. In fact, adding parentheses to this expression changes it completely. Whoops. Oh, I see what happened here. So in fact, this evaluates to true. Sorry, this evaluates to true. And the reason why it does that is because this is in fact a ternary comparison operation. This is, yeah. Which you could see here if I hadn't screwed up the syntax. So this is exactly the same code as A less than B less than C. And I see a lot of skeptical faces, and that's totally reasonable. So let's look at the bytecode. So here is false is false is false. Now don't blink while I change the slide. Here's A less than B less than C. So you don't have to know anything at all about bytecode to see that this is exactly the same structure. So even if you're not used to looking at this at all, it just like leaps off the page. And so we can use this internal view to become much more confident about the way that the code behaves, that our mental model is correct, or as it turns out, basically I think everyone in the room guessed the wrong answer. But here's what's going on here. I did this too the first time I saw this. The other thing that's kind of fun is we can see that comparison operators are parameterized. So I'll just leave that there as a little nugget we can come back to. Okay, so let's talk about the second strategy, experimentation. So we've been talking a little bit about thinking about code scientifically, and the two examples so far are naturalism and astronomy, and both the things that those two things have in common is it's very hard to do experiments. But we're programmers, and so we don't actually suffer under that restriction. And there are lots of ways about learning about an unfamiliar code base in front of you, other than just looking at it different ways. You can run experiments. You can make hypotheses and test those hypotheses. And one way you can test your hypotheses is with measurements. There are a ton of different measuring tools available. One simple one to start with is time it for measuring the speed of code snippets. And in this example, I'm testing whether it is faster to call the method sort or to call the built-in sorted on a list. There was a really interesting example in David Beasley's talk yesterday, where he was timing execution of different versions of concurrent code. And through just like something that was making requests in a loop and measuring how many requests per second he could get, he led us to an interesting piece of information about how the GIL prioritizes tasks that I think is the opposite of what most people would expect it to do. And so just doing this simple measurement and having a theory for how the GIL should be doing prioritization, we can actually test that. I think it's particularly important in this sort of experimentation to have a hypothesis that you're testing. Otherwise, it's pretty easy to kind of accumulate a lot of numbers that don't really mean anything or tell you anything new. And I do want to say, please don't time things and then go do things that way, always irrespective of style. This sort of minuscule timing optimization is almost never a good guide for how you should phrase a line of code. Now, another great way to run experiments is with tests. So you're saying to yourself, okay, I'm reading this code base, and I think that this particular invariant always holds. So write a test that proves that, or that shows that for a number of cases. Then you can build up these small blocks of knowledge into a much more robust understanding of the system. And this will probably be slow the first time that you do it. And it does reintroduce the sort of tooling and installation hell that we'd hoped to avoid. But I think it's worth it. And the reason why I emphasize this is not because it has never occurred to any of you to write tests, but because I think my threshold for when you should start writing tests is much lower than you might have heard. I think if you're spending more than like an hour with CPython, you should try writing a test. And you don't necessarily have to write a formal test either. You can, for example, use the function that you're looking at, or like remove a piece that seems important and see if it falls over in the way that you expect it to. And this is something that I personally am often bad at. I often want to have a very complete mental model of the system before I go in and start making changes. And this is an inefficient decision, like almost every time. It would be much faster for me to start making changes, start writing tests, build up my mental model along the way, and then that's code that I probably won't keep. Like, you know, I will end up building that mental model, throwing away all the code, and then maybe making a change if that's what I'm trying to do. But again, since we're not talking about contributing or anything today, like you should take your copy, you can take your copy of CPython and make it do whatever you care about. It's just to increase your understanding and then throw it away. So let's put this all back together, and I want to leave a couple of minutes for questions about these strategies and/or about the random module if people are interested. And when you're starting to dig into the Python code base, don't read it. Interact with it in some other way. And I love digging around in Python source. I find it really deeply satisfying to be increasing my understanding. And it's something that I recommend everyone. So I hope you do this, and I hope you do this in a really interactive and playful way. And one of the great things about open source software is that you have your own copy of the code in front of you. And you can poke it and prod it and run experiments and make silly or ill-advised changes. And some of the most interesting and objectively really fun projects that I've had were extremely ill-advised. And they were great ways to learn. So I encourage you to go out and download a copy of Python source if you don't already have one and start not reading it. Thank you.
Hi. Oh, yep. Hi. I consider myself a fairly jaded old Python programmer, so I just want to say thanks because I learned something today. My question, though, is, so why does choice look like a method?
If only I had a slide for that. So this is a really interesting model, I think. So basically, the choice is implemented as a method on the random class. And when you import the random module for the first time, you get an instance of that class. And then in that module, it rebinds all of the methods as function names. So you see like seed equals instance.seed and random equals instance.random and so on. And then there's a comment that explains the rationale, which basically says you want to preserve the ability for the Python programmer to reseed the random module. And that's what happens in the init function of this random class. So we do want to preserve that, but random.choice, I think, is maybe most often used in like text adventure games by beginners. And so we don't want to impose this cost on new Python programmers or Python programmers who don't need special control over the random module. So this is the way that's implemented, and then the names are rebound, and _all is defined in the method, so you don't get kind of junk that doesn't belong there when you do a star import. Other questions? Great, thank you.